Pleasant day to everyone. Today we're going to discuss another method of solving systems of linear algebraic equations. So this method is what we call pivoting, which is under the Gaussian elimination method. So for Gaussian elimination with partial pivoting, this is now a method used to solve simultaneous linear equations which follows the form of ax equal to b. So given now, let's see, four equations with four unknowns, matrix A will basically have 16 elements which would represent the coefficients for each unknown variable and for each equation. And then for matrix X, that will simply be a column vector of the unknowns or the variables, and matrix B is a column vector of the constant values in our equation, or what we call your independent variables or independent terms. So in Gaussian elimination with partial pivoting, basically we have two steps that we follow. The first step is your forward elimination, wherein our general equation or general matrix form Ax equal to B is converted to matrix equation Ux equal to C. So in this transformed equation through forward elimination, matrix A now becomes matrix U, which is simply an upper triangular matrix, and matrix C is simply an altered version of your vector column or column vector B. Okay, so in that case, matrix U now will have this form. So as you can see, we have reduced all elements below our diagonal equal to 0. But for U11, U11, U22, U33, U44, or all elements in the diagonal will have a value and not necessarily equal to 1. So for matrix X, that will not be unchanged, and matrix C will still be constant values, but it will have variations now because of our reduction of our matrix A. So from this matrix or this matrix equation, we can now derive an equation for each of our values. So we'll have now U11 x1 plus U12 x2, U13 x3, U14 x4 is equal to C1. So it's just an application of our multiplication method. So next we have U22 x22, x23 x3, U24 x4 equal to C2, u33 x3 plus u34 x4 equal to c3, and u44 x4 equal to c4. So as you can see, from our derived equations, we'll now be able to compute for the values of our unknown variables or unknown terms. Thus, we'll now be able to apply the second step in partial pivoting, which is our backward substitution. So backwards, since we are going to start with our last equation, or we'll simply be solving it through simple algebra. So x4 now can be computed as c4 divided by u44. And since we have computed for x4, you can substitute that in this equation. So x3 can be computed as c3 minus u34 x4 all over u33. And then we have x2 is equal to c2 minus u23 x3 minus u24 x4. So you are your computed coefficients, and x3 are your computed values for the unknown x. So divide it by u22, or the coefficient of the unknown that we are solving. And then for this example, lastly, we have x1 is equal to c1 minus u12 x2 minus u13 x3 minus u14 x4 all over u11. So if you are going to observe these four equations now, generally, for partial pivoting, we can now apply our general equation, or we could derive our general equation, wherein xi is now equal to ci minus the summation of uij xg from g, which is equal to I plus 1 until the value of n. And multiply this now by 1 over uij. This is applicable now for all values of I, which is from 1 until n minus 1. And then xn is now equal to cn divided by u sub m. And this is applicable for I values equal to n. Remember, I are our terms of, is in terms of our rows or our columns. G will be in terms of our rows. N is equal to the number of columns, and m is equal to the number of rows. Okay, so you don't have to memorize this because you can simply solve our variables later on through simple algebra. So to understand Gaussian elimination with partial pivoting, let us have some examples. So let's say we are given here matrix 0, matrix A with elements 0, 1, 2, 3, 0, 1, 4, 12, 1, 1, 1, 1, 1, 2, 4, 8, which is multiplied to a matrix of unknown variables x1, x2, x3, x4, and is equal now to negative 0.2, 0.8, 1.5, and 1.2. Okay, so in partial pivoting, what we want to do is that our augmented matrix, which is the matrix of your coefficients, should have now its leading element, A11, or your pivotal element, should not be equal to 0. So in that case, we call now 0, which is the diagonal location of K, or the first diagonal location, K equal to 1. So in that manner, since this is 0, what we want to do is to interchange this or swap this to another row which will have a value not equal to 0 or greater than 0. So we now check all our elements under 0, your A11 or your k equal to 1 by partial pivoting, meaning we now find all the values of the elements in row under k which should be greater than your lead element or your pivotal element. So in this case, we have two rows having greater values. We have row 3 and row 4. So since pareho naman sila, what we can do is to choose either of the two. But to have consistency in our equations, we can use whatever the first value is or the first column given. Yun ang i-interchange or isa-swap natin dito sa first row ninyo. Okay? So, for the highest magnitude now, so we have the same values here. So, we'll now only consider the first one. So, we swap now rows 1 and rows 2. So, we'll now have a new matrix 1, 1, 1, 1, 1.5. And then we have the third row becomes 0, 1, 2, 3, negative 0.2. So what happens if we have, for example, in this section, we have 3, 2, 1. So ang pipiliin ko is yung row na may pinakamalaking value. So kung 3 ito, yung 3 ang ililipat ko doon sa ating lead element. Okay? So, we have to transfer the maximum or highest magnitude in our pivotal element or your lead element. Okay? So, we have now applied the first part of your partial pivoting, which is forward elimination. This is our first element or first matrix. So what we want to do is that all the elements under your lead matrix or lead element is equal now to 0. So in that case, we can solve this as R4 minus R1 or R1 minus R4. It will just give us the same value. So in our solution, we'll have R4 minus R1, which will now lead us to 0, 1, 3, 7, negative 0.3. So, sige. Okay? So, na-change na yung last column. So, next, we now move on to our second diagonal location, 2, which is A22. Okay. So, in here, lahat sila magkakapareho. So, meaning, no need to change our rows. So what we will do here now is to reduce the elements under diagonal location 2. So with that, partial pivoting, wala na tayong masaswap. So we now proceed to elimination. And elimination, we eliminate this simply by R3 minus R2 and R4 minus R2. Or you can do otherwise, R2 minus R3 or R2 minus R4. We will still arrive at the same final answer later on. Okay? So with that, we'll now have for the third row, so 1 minus 1 is 0. 4 or 2 minus 4 is negative 2. 3 minus 12, negative 9. Negative 0.2 minus 8, negative 1. And then for the fourth row, that will give us negative 1, negative 1, negative 5, and negative 1.1. So after elimination, we move to check our diagonal location 3, which is A33. So it's negative 2. So we check now here our element below your diagonal. So we now apply partial pivoting. Negative 2, negative 1. Compare natin. Absolute values. 2 is greater than 1. So no need to pivot or no need to swap our rows. Okay? So next, we now apply your elimination. So elimination of negative 1 will be done by 2R4 minus R2. So in that case, we'll now have negative 2, 0, negative 9, negative 1, negative 1, negative 1.2. So we have already converted all the elements under your diagonal equal to 0. So from here, we are finished with your forward elimination. Then we can now apply your backward substitution. So in order to do that, we rewrite our equation. So we'll have now x1, x2, x3, x4 is equal to 1.5. For the second equation, that's now x2 plus 4x3 plus 12x4 equal to 0.8. Third equation is negative 2x3 minus 9x4 minus 1 or equal to negative 1. And lastly, we have negative x4 is equal to negative 1.2. So from these four equations that we have derived through partial pivoting, we'll now be able to solve for our variables. So for x4, that is now negative 1.2 divided by negative. So x4 is equal to 1.2. For x3, that is negative 2x3 equal to 9 times 1.2 minus 1, giving us a value for x3 equal to negative 4.9. And then x4, x3, substitute in this equation. So we'll now have for x2, that's x2 plus 4 times negative 4.9 plus 12 times 1.2 equal to 0.8, wherein x2 now is equal to 6. And lastly, we have x1 plus x2 plus x3 plus x4 is equal to 1.5, giving us a value for x1 equal to negative 0.8. Okay? So another example for partial pivoting. So for the linear system, we have x minus y plus z equal to 2, negative 6x plus y minus z equal to 3, 3x plus y plus z equal to 4. So what we do is to first write our augmented matrix. So I'll have 1, negative 1, 1, 2, negative 6, 1, minus 1, 3, 3, 1, 1, 4. So for our partial pivoting, what we do is to look first for the maximum value of the element that we have, absolute value. So we have here negative 6. So meaning this negative 6 should be our lead element or your lead pivot point or pivotal element. So what we will do is to swap now R1 and R2. So we'll now have 6, negative, 1, negative 1, 3, 1, negative 1, 1, 2, 3, 1, 1, 4. Okay? So, after pivotal or pivoting, so we now reduce or eliminate the elements under your lead element. So this will be reduced using 6R2 plus R1. So we'll now have 0, 5, negative 5, and 15. And then for the next row, we reduce this by the equation 2R3 plus R1, or that is now 2 times R3 plus R1 is 0. 2 times R3 plus R1 is 3. 2 times R3 plus R1 is 1. And 2 times R3 plus R1 is 11. Okay? So next, we move on to our second diagonal location, which is negative 5. Comparing now their absolute values, 5 is greater than 3, so there is no need to interchange or swap our remaining rows. So with this, we now continue with elimination. So we eliminate this by 3R2 plus 5R3, which will now give us a simplified matrix of 0, 0, 20, 100. So from this case, we have already converted or reduced the elements under your diagonal to 0. So we can now rewrite our equations. So that will now be negative 6x plus y minus z equal to 3. Negative 5y plus 5z equal to 15. And 20z equal to 100. So from these three equations, we can now solve for the variables x, y, z. Z now is equal to 5, y is equal to 2, and x is equal to negative 1. To understand Gaussian elimination with total pivoting, let's have an example. So let's look at the first example that we also solve using partial pivoting. So in partial pivoting, transfer ko lang or ang kinonsider ko lang is the element that has the maximum or highest value in terms of the rows. For total pivoting, what we are going to consider is the highest value of the element for the entire matrix. Okay? So for your augmented matrix, again, we have this one. So from here, we look for the maximum or the highest element, and that is 12. Okay? So if there are negative values, we consider their absolute value. Okay, so even if it's negative 12, it will still be our maximum considering its absolute. So for 12 element, so what we do is to swap first our rows, so row 1, row 2. So we'll have this new matrix, and then this maximum value now will become our lead element or your pivot element. So we do that by interchanging row 1 and or column 1 and column 4. So this will now be our working matrix for the Gaussian elimination with total pivoting. So note that the positions or the order of your variable x will now also vary since we have also interchanged our columns. So the first column now will be for your x4 and the last column will be for x1. Okay? So what we do, as we have already established our lead element, which is the maximum value or maximum element here. So next is to eliminate now the elements under the first column. So we'll have this as 4R2 minus R1, 12R3 minus R1, and 1/2 R4 minus 1/3 R1. So this will give us now the following matrix. And then next is we eliminate these elements by using 3R3 minus 11R2 and 3R4 minus 2/3 R2. Okay, so take note that for total pivoting, there is now no need for us to interchange your rows for the maximum elements, since we have already also considered our columns. Okay, so for total pivoting, once you have established your maximum element in our lead point or lead element, then we continue or we solve it through elimination agad. No more pivoting. Okay? So with these equations, we'll now arrive at a new matrix. And then lastly, we reduce the last element under your diagonal. So we eliminate this by 20 R4 minus 2/3 R3. So we have now reduced our matrix into a upper triangular matrix. So from here, we now rewrite our equations. We'll have 12x4 plus x2 plus 4x cubed equal to 0.8. We have 3x2 plus 4x3 equal to negative 1.6. Negative 20. X cubed or x3 plus 36x1 equal to 69.2. And 6x1 minus negative 4.8. So, by back solution or back substitution, we can now solve for our unknowns. X1 is equal to negative 0.8. X3 is equal to negative 4.9. And then we have X2 is equal to 6. And lastly, we have X4 is equal to 1. So another example for Gaussian elimination with total pivoting. So for the given linear system, negative 2x plus 3y minus 2z is equal to 10. 2x plus 2y minus z equal to 9. 2x plus 6y minus 3z is equal to 23. So for this, again, we start off with our augmented matrix. So I'll have negative 2, 3, negative 2, 10, 2, 2, negative 1, 9, 2, 6, negative 3, 23. So again, we'll look for the maximum value of the elements. Okay, so we disregard our 4 pure constants. So we only look for the values here. And we have 6. So what we do is we put 6 in our lead point or lead as the lead element. So I do that by swapping row 1 and row 3. So we'll have 2, 6, negative 3, 23, and our 3 will become negative 2, 3, negative 2, and 10. So hindi pa siya ang ating lead elements. So we now swap x and y. So we'll have now 6, 2, 3, 2, 2, negative 2, negative 3, negative 1, negative 2, 23, 9, and 10. So this one now will be our working matrix. So we have established our lead element or our pivot element. So what we do now is to reduce the elements under it. So by elimination, we'll have now 3r2 minus r1, which will give us 0, 4, 0, 4. And then next we have 2r3 minus r1, giving us the elements 0, negative 6, negative 1, and negative 3. And then we reduce the last element. Okay. So using this equation, we can now reduce it again to 0, 4, or that's 0, 0, 4, negative 12. So we can now rewrite a equation of our matrix. We have negative, it's positive 6, y, 2x minus 3z equal to 23, 4x equal to 4, and 4z equal to negative 12. So from these equations, we'll now be able to solve for z, which is negative 3, x is equal to 1, and lastly, we have y is equal to 2. Okay? That is for pivoting method under Gaussian elimination or Gauss elimination. So, before we end, let us again review. Pag Gaussian elimination without pivoting, we reduce our matrix to a triangular or upper triangular matrix with the diagonals equal to 1. Okay? So we don't have to establish a lead element or a pivotal element. So kahit alin doon pwede nating gamitin. And then for nag-swap lang tayo sa may elimination without pivoting ng rows because we want to simplify our solution. So kung may 1 doon, saka lang tayo nag-swap. Pero kung walang 1, doon sa given natin for the first column, then we continue it by reducing it to a value of 1. And then, for partial pivoting, you look for the maximum value or maximum element along the first column. And then, that's the time we apply pivoting or swapping. And then, after that, we reduce the elements below it to 0. And then, next step is to check on your second diagonal element if it has elements under it which is greater than your current diagonal element, then that's the time we apply swapping or interchanging. And then after pivoting, apply elimination, reduce our elements under your A22 to 0. Then we move on to A33. And then check again if the elements below A33 is greater than your A33. If it's greater than A33, then we apply your pivoting. Kung hindi, then we go on with elimination. And then for total or complete pivoting, hanapin natin yung maximum doon sa buong matrix natin. And then, yung maximum, yun yung gagawin nating lead element or your pivotal element by switching or swapping your rows and columns. And then, same procedure with partial pivoting already, or same procedure with the Gauss elimination without pivot. So, once you have established your lead element, then dire-diretso na siyang elimination ng elements below the diagonal.